In the today's class, we'll discuss about the basics of molecular spectroscopy. So if you consider a molecule, the molecule can be found in ground state or any excited state, depending on the energy of the molecule. So apart from the ground state, that is the trivial case, a molecule can be in the higher energy state, and transition between the various energy levels gives rise to observed molecular spectra. So that is in accordance with the quantum mechanics or basic Bohr's theory. The transition of molecule from higher energy state to the lower energy state gives rise to emission of radiation, and that leads to the observation of molecular spectra. The energy of the diatomic molecule, if you consider a diatomic molecule, then energy of that diatomic molecule consists of three different energy combinations. Otherwise, it is arising because of three different modes of motion. One is the electronic configuration of the electrons in the molecule. The electrons are revolving around the nucleus in a particular orbit, and that motion of electron gives rise to the energy for the molecule. Okay, and that is called as electronic energy. Second one is the vibration of the atoms about the equilibrium position. So in a molecule, the atoms are not stationary, they are going to vibrate continuously with respect to certain position. So with respect to the equilibrium position, the atoms are going to vibrate. There are different modes of vibration, and these vibrational motion gives rise to energy for the molecule. That is the second part of the energy. The third part is the rotation of molecule as a whole about its center of mass. So about the center of mass, the molecule can rotate in a different direction about certain axis. It can rotate. Because of that, it will acquire some moment of inertia, and that leads to the rotational energy for the molecule. So basically, three modes of motion are the electronic motion, the vibrational motion of the atoms in a molecule, and rotation of the molecule. These three gives rise to total energy of the molecule. Therefore, we can find out the total energy of the molecule as E equal to EE plus EV plus ER, where EE is the electronic energy, EV is the vibrational energy, and ER is the rotational energy of the molecule. So here in this particular expression, this electronic energy, vibrational energy, and rotational energy all are quantized, and they are in accordance with the quantum mechanics. They can have only discrete energy values. Okay, that is the meaning of quantization of energy. And it is observed that the electronic energy EE is greater than vibrational energy, and which is going to be greater than the rotational energy. And here the value of electronic energy is highest, then vibrational energy is little bit lesser, and the rotational energy of the molecule is smaller one. So in comparison with these three modes of motion, let us consider the rotational motion. If the molecule remains in a ground state, ground level, the electronic and vibrational energies, and if it suffers transition between different rotational energies, we get the pure rotational spectrum. Okay, so let us take the molecule is in the ground electronic state and ground vibrational state. That is, vibrational energy is minimum, the electronic energy is also minimum for a molecule. If within that energy state, the rotational energy, if they are different, then molecule can make the transition from higher rotational energy level to the lower rotational energy level, and that gives rise to pure rotational spectrum. Already I have told you the rotational energy of the molecule is least. That's why there is a small changes in the energies of the molecule because of the transition between the rotational energy levels. So these spectra, that is rotational spectra, are observed in the microwave and far infrared region. So they are having lower energy spectral lines. They are having lower frequency spectral lines. Okay, so these rotational spectra comes in lower energy side. If the molecule remains in the ground state level of the electronic energy, okay, let us take the molecule is in the ground electronic energy state. If transition occur between different vibrational and rotational energies, then we get the vibration rotation spectrum of the molecule. Okay, so if molecule make the transition between vibrational energy levels and rotational energy levels, then we'll get the vibrational rotation spectra. Sometimes it is also called as RV spectrum, rotation vibrational spectrum. So these spectra are observed in near infrared region. So almost it is observed in infrared region. This vibrational spectra is observed in infrared region of the electromagnetic spectrum. If the transition occurs between different electronic, vibrational, rotational energy levels, if all energies are considered, then we'll get the electronic spectrum of the molecule. And for a molecule, we'll observe the band spectrum as a molecular spectra. The electronic spectrum of the molecule is going to be band spectrum. So it is consisting of large number of spectral lines together. So this spectra is observed in visible and ultraviolet region. The electronic spectrum is observed in ultraviolet region of the electromagnetic spectrum. Now let us consider the theory of origin of the pure rotational spectrum of the molecule. Suppose only rotational motion is considered, how the energy of molecule is going to be found, and the transition between the energy levels gives rise to the rotational spectrum. How this rotational spectrum look like? Okay, we'll consider that. Let us consider the diatomic molecule consisting of atoms of masses m1 and m2 separated by a distance r0. Okay, so m1 and m2 are the masses of the atoms of a diatomic molecule, and these two atoms are separated by the minimum distance, okay, otherwise the equilibrium distance r0, okay, which is nothing but the bond length of the molecule. So this is the simple diagram I can imagine. So it is a diatomic molecule consisting of two atoms, and one atom is having mass m1, another atom is having mass m2, and distance between the centers of atoms is going to be r0, and that is considered to be equilibrium distance or bond length of the molecule. Now m1 is greater, mass of the first atom is greater, that's why center of mass of the molecule lies near m1. So this point C represents the center of mass or center of gravity of the molecule, where the moment of mass is going to be 0. Let us consider the center of mass from m1 is situated at distance r1 and m2 is situated at r2 from the center of mass. Okay. So in this figure, we have represented the diatomic molecule, and we can imagine the diatomic molecule which can rotate about its center of mass according to this particular figure. It can rotate about the center of mass in this direction, like this it can rotate, or like this it can rotate. So different combinations are possible. Okay, about x-axis it can rotate, about y-axis it can rotate, like that. Okay. Now let R1 and R2 be the distances of M1 and M2 from the center of masses. Okay, already I have told you. R1 is the distance of M1 from center of mass. R2 is the distance of M2 from the center of mass. Now from this figure, definitely the equilibrium distance R0 is equal to R1 plus R2. Okay, where R1 and R2 represent the distance of atoms from the center of masses, and total distance R1 plus R2, which is equal to the equilibrium distance R0. Now we have to find the moment of inertia of this molecule about an axis passing through its center of mass and perpendicular to the line joining the atoms. Let us consider an axis which is passing through center of mass and which is perpendicular to the bond length. About this axis, this molecule can rotate. Then what is the moment of inertia? I have to find out. So total moment of inertia will be equal to moment of inertia of first atom plus moment of inertia of second atom. So moment of inertia of first atom about the center of mass is m1 r1 square. And for second atom, it is m2 r2 square. It is mass into distance square. Okay, where distance should be the distance from the axis of rotation. Since axis is passing through the center of mass, the distance of first atom from the center of mass is r1. Distance of the second atom from the center of mass is r2. So total moment of inertia I will be equal to m1 r1 square plus m2 r2 square. Now from the definition of center of mass, moment of masses of atoms about the center of mass should be equal to 0. Okay, so at the center of mass, the molecule comes to balance. Okay, so it comes to balance means mass is concentrated at center of mass. So it means that moment of masses of these atoms about the center of mass must be equal to 0. What do you mean by moment of mass? Moment of mass is mass into distance from the center of mass. m1 r1 minus m2 r2 should be equal to 0. The negative sign is taken because m2 is situated on the opposite side. Okay, if you take this as positive axis, then the opposite side should be negative axis. So if r1 is taken to be positive, it is from on left side, then r2 should be taken negative. It is on the right side. That's why the total moment of masses, algebraic sum of moment of masses should be equal to 0. That gives rise to m1 r1 minus m2 r2 should be equal to 0. So it implies m1 r1 that should be equal to m2 r2. Take this as equation 1 and we'll get m1 r1 m1 r1 equal to m2 r2. Now substitute in the moment of inertia expression. Substitute for m1 r1 here. Okay, and substitute for m2 r2 here. So I will be equal to, for m1 r1, I will substitute m2 r2 into r1. We have m1 r1 square. It can be rewritten as m1 r1 into r1. So m1 r1 is replaced by m2 r2 into r1 as it is, plus m2 r2 is replaced by m1 r1 into r2. Then we can take r1 and r2 as a common factor. So I will be equal to r2 r1. In the bracket, you will get m2 plus m1. Okay, so we'll get moment of inertia equal to r2 r1 into m2 plus m1. Take this as equation 2. Now we have the equilibrium distance r0 equal to r1 plus r2. Okay, so I can write r2 is equal to r0 minus r1. We know r0 equal to r1 plus r2. Therefore, r2 will be equal to r0 minus r1. Now substitute this in equation 1. Substitute for r2 in equation 1. You will get m1 r1 equal to m2 r2, and that can be rewritten as m2 into r0 minus r1. I have substituted for r2. Okay, m1 r1 as it is, m2 r2 is there on the right hand side. For r2, I can substitute r0 minus r1. So we'll get m2 into r0 minus r1. Solving for r1 and r2. Let us solve for r1 using this expression. You have m1 r1 equal to m2 into r0 minus r1, this equation. Okay, m1 r1 equal to m2 into r0 minus r1. You open this bracket and get the expression for r1. Okay, so you'll get m1 r1 equal to m2 r0 minus m2 r1. Okay, m1 r1 equal to m2 r0 minus m2 r1. This implies m1 r1 plus m2 r1. You take this term to the left hand side. That should be equal to m2 into r0. Okay, now get the expression for r1. You take this r1 as a common factor in the bracket. You will get m1 plus m2. That should be equal to m2 r0. Okay, therefore r1 equal to m2 r0 divided by m1 plus m2. You have got the expression for R1. So R1 equal to M2 into R0 divided by M1 plus M2. Similarly, you can get R2. Okay, the expression for R2 can be obtained in the same way, and you definitely will get R2 equal to M1 R0 by M1 plus M2. Note the difference here. R1 equal to M2 R0 by M1 plus M2. R2 equal to M1 R0 by M1 plus M2. Definitely you are going to get this expression. R1 and R2 are obtained like this. Now substitute these values of R1 and R2 in equation 2, that is moment of inertia equation. Okay. So substitute for R1, substitute for R2. So I is equal to, now for R1, you have to substitute M2 R0 by M1 plus M2 into, for R2, you have M1 R0 by M1 plus M2 into M2 plus M1. Okay, basically you have got a moment of inertia I equal to R1 R2 into M2 plus M1. Okay, we have substituted here. Now M1 plus M2 gets cancelled. Okay, one term gets cancelled, and finally you will get I is equal to M1 M2 into R0 square divided by M1 plus M2. So this is the expression for moment of inertia in terms of the masses of the atoms into and the internuclear distance or bond length. Okay. And we can write this expression as I is equal to mu into R0 square. This product of M1 and M2 divided by sum M1 plus M2, this ratio can be expressed as mu, which is called as reduced mass of the molecule. So here we have substituted mu is equal to M1 M2 divided by M1 plus M2, which is called as reduced mass of the molecule. And this equation gives the moment of inertia of diatomic molecule in terms of the atomic masses and the bond length. If you know the atomic mass M1 and M2, and if you know the bond length, you can find the moment of inertia. Or if you know the moment of inertia and the masses, if you know, then definitely you can find the bond length of the molecule, and that is going to be used in the RV spectrum experiment done in the 604 laboratory. Now you have to find the angular momentum of the diatomic molecule, because you have to find the energy of the molecule. Now we have found the moment of inertia. Now the angular momentum of the diatomic molecule is related to moment of inertia as L is equal to I omega, where L is the angular momentum of the molecule, I is the moment of inertia, omega is angular velocity. Okay, angular velocity of the rotating molecule. Remember, this corresponds to rotation of the molecule, and here omega is the angular velocity of the rotating molecule. Now the angular momentum is quantized. It is not discrete, it is not continuous, it is discrete and quantized. And according to quantum mechanics, this angular momentum L can be written as square root of j into j plus 1 into h by 2 pi. So basically, angular momentum of the molecule is integral multiple of h by 2 pi, where h is Planck's constant. That is in accordance with quantum mechanics. And this square root of j into j plus 1 represents the quantum number. Okay, otherwise it is called as eigenvalue. Here j is called as rotational quantum number. In this particular expression, h is Planck's constant, j is rotational quantum number, and j takes integer values from 0, 1, 2, 3, etc. Okay, j takes the values from 0, 1, 2, 3, etc. Now, the rotational kinetic energy is given by E is equal to half I omega square. Okay, we have got the expression for angular momentum. Now we have to get the expression for energy. So energy is basically equal to half I omega squared. Okay. Here I is moment of inertia, omega is the angular velocity. Okay. Now expressing in terms of L, express this particular expression in terms of angular momentum. We know that L equal to I omega, therefore I equal to L by omega. We can write E equal to L square by 2I. Substitute for I omega, that's all. Okay. So basically, it is in terms of I, and we can express energy in terms of angular momentum L. Okay. So you'll get E is equal to L square by 2I. Now substitute for L and substitute for I. Okay. So you will get the total energy of the rotating molecule equal to L square. L square is written as J into J plus 1 into H square divided by 2 pi square. So that will give you 4 pi square into 2I. 2I is here. Into 2 means you will get 8 pi square into I. It is in terms of joules. So E equal to J into J plus 1 H square divided by 8 pi square into I. That is expressed in joules. But basically, the energy in spectroscopy, okay, is expressed in terms of centimeter inverse. That is in wave number units. Okay. This expression gives the allowed quantized rotational energy levels in joules. It is expressed in joules. Now we have to express this in terms of the wave number unit. In the study of spectra, it is required to consider the difference between energies of energy levels, particularly corresponding frequency nu is equal to delta E by H in hertz or wave number unit. Okay, so if you express frequency in terms of wave number, okay, so that is nu bar is equal to delta E by Hc. Okay, what you have to do? You have to divide the energy by C. That will give you the frequency in nu in hertz into centimeter inverse. Here H is the Planck's constant and C is the velocity of light in vacuum expressed in centimeter per second. You have to remember this. C must be expressed in centimeter per second, that is 3 into 10 to the power 10 centimeter per second. Okay. So what you have to do? Rotational spectrum is discussed in wave number units, and hence we have to express energy in centimeter inverse. Therefore, the energy in wave number units is given by EJ, that is energy in wave number unit, is equal to E by Hc. We have to divide the energy by Hc, that will give you energy in wave number unit, where this E is energy in joules. If you want to convert the energy from joule to wave number, just you have to divide it by Hc. So therefore, if you divide it, you will get Ej, that is energy in wave number unit, centimeter inverse, equal to J into J plus 1 H divided by 8 pi square I into C. If you divide it by Hc, here there is a H square, H gets cancelled, only C will be observed in denominator. This is the final expression for energy of the diatomic molecule. Okay. So energy of rotating diatomic molecule or rotational energy levels of the diatomic molecule is given by Ej is equal to J into J plus 1 H divided by 8 pi square IC, that is in centimeter inverse unit. So this is the energy of rotating diatomic molecule or rotational energy of the diatomic molecule. This can be expressed as Ej is equal to B into J plus 1. Here you can observe these are all constants. H is constant, pi is constant, moment of inertia is constant for a given diatomic molecule. C is velocity of light in vacuum, that is also constant. Okay, so definitely I can write the energy as B into J plus 1. I can keep this as it is, and this term can be replaced by the term B. And here J can take the values from 0, 1, 2, 3, etc. And here B is equal to H by 8 pi square into IC, which is called as rotational constant. Okay. So B is called as rotational constant, and it is having the expression h divided by 8 pi square I into C. To understand the pure rotational energy levels in the rotational spectra, we have to determine energies of energy level. What is the energy of first level, energy of second level, you have to find. So for J equal to 0, basically this energy of first level, second level can be found by putting the values of J equal to 0, 1, 2, 3, etc. For J equal to 0, it represents ground state. Okay. And here for J equal to 0, E0 is equal to 0. So ground rotational energy is 0. For J equal to 1, if you put J equal to 1, EJ will be equal to 2B, because J is 1, 1 into 1 plus 1, 1 plus 1 is 2. So you'll get E1, the first ground state, that is first excited state of the rotational energy level is 2B centimeter inverse. For J equal to 2, what is the value of E2? Put J equal to 2 here. So 2 into 3, it is 6. So E2 will be 6B centimeter inverse. For J equal to 3, what is E3? Put J equal to 3 here. You will get a 3 into 4, that will be equal to 12B centimeter inverse, and so on. Similarly, you can find the next energy level values. If you represent these energy levels by calculating the different energy values, definitely the energy levels look like this one. The first energy level for J equal to 0, energy is 0. For J equal to 1, energy is 2B centimeter inverse. For J equal to 2, it is 6B. J equal to 3, the value of energy is 12B. J equal to 4 gives you total energy 20B. So this is how the energy levels of the rotating molecule are observed. These energy levels are not equidistant. The separation between first two energy level is 2B. Next energy level is observed at 6B. What is the difference between these two? It is 4B. The next energy level is observed at 12B. What is the difference between second level and third level? It is total 6B. The next two energy levels are separated by the value 8B centimeter inverse. So that's why the rotational energy levels are having the increasing separation between them. So these are the energy levels, and what are the allowed transition and how rotational spectrum look like. Suppose a transition takes place from one level to the another level, that gives rise to absorption of electromagnetic radiation or emission of the electromagnetic radiation. And here in this particular energy level, if molecule goes from ground state to first excited state by absorbing the electronic radiation, then it will absorb the energy 2B, because that energy is required for the molecule to go from 0 energy to the 2B energy. This is another allowed transition. The molecule can jump from 2B energy to 6B energy. That is first excited state to second excited state. What is the difference between these two? It is 4B, and that spectral line is observed here. Next is 6B, next is 8B, next is 12B, that runs like this. Okay, so here the rotational energy levels are giving rise to, or rotational spectrum gives rise to lines which are separated by 2B distance. So first line is observed at 2B, second line is observed at energy or frequency 4B, next line is at 6B, 8B, 12B, etc. So this is in centimeter inverse. Okay. So these transition gives rise to rotational spectrum. Remember, these are energy levels and transition. This is the spectrum observed. Okay. Absorption lines you can observe with equal distance lines. Okay. Now this is how you can observe the spectrum, and how this spectrum is obtained. That is using the selection rules. Okay. So selection rules are obtained by solving the Schrodinger equation according to quantum mechanics. Basically, for rotational energy levels, the selection rule is given by delta J equal to plus or minus 1. Okay. So delta J represents change in rotational quantum number for a transition. You consider first transition. J is changing from 0 to 1. So delta J, change in J is -1. For second one, it is going from J equal to 1 state to J equal to 2 state. What is the change in J value? It is -1 like this. So transition is allowed between neighboring states only. The molecule cannot go from 0 to third state or fourth state directly. It can go one by one. It can go from 0 to 1, or it can go from 1 to 2, 2 to 3, like that. So only the change of J value allowed is equal to ±1. The reverse transition is possible. That gives you emission. Okay, so the increasing J value gives you absorption, decreasing J value gives you emission. That's why ±1. The transition for which J can change by ±1 are only allowed. Okay, that is the selection rule for rotational energy level and rotational spectrum. Now we'll find out what is the first spectral line in the rotational spectrum is due to the transition of molecule from J equal to 0 to J equal to 1 level. This is absorption. Then the wave number of first line, that is equal to difference between energies, that is E1 minus E0. So first line is observed to be E1 minus E0. What is E1? It is 2B. What is E0? E0 is 0. You will get the wave number of first line is 2B centimeter inverse. Similarly, the second line corresponds to second transition, that is nu2 bar is equal to E2 minus E1. So that is equal to 4B centimeter inverse, because the E2 is 6B, E1 is 2B. So it will be 4B centimeter inverse. Then third line is nu3 bar, which is equal to E3 minus E2, which is equal to 6B centimeter inverse, and so on. So wave number of spectral lines are going as 2B, 4B, 6B centimeter inverse, and so on. Therefore, in pure rotational spectrum of the diatomic molecule, it consists of the spectral lines of wave numbers 2B, 4B, 6B, 8B, so on. Okay. Therefore, the spectral lines are equidistant and separated by 2B inverse. And you can recall the experiment on RV spectrum where you have taken the slope of the straight line obtained equal to 2B. So B will be equal to slope divided by 2. This is the reason behind that. Okay. Because in slope, that gives you the distance between consecutive lines or neighboring lines, and distance between the lines in rotational spectrum is equal to 2B. If you know the distance between the two lines, you can find the value of B. If you find the value of B, it is possible to find the moment of inertia, and finally you can find the bond length of the molecule. So this is the theory of the rotational spectrum and how rotational spectrum can be expressed in accordance with the quantum mechanical theory.